Welcome to the Explainer. All right, let's get right into it because today we are looking at what could be a huge shift in artificial intelligence. We're talking about a brand new model, one inspired by the brain, that can solve logic puzzles that leave today's biggest and most powerful AIs, well, completely stumped.
But first, here's a weird thing, isn't it? You've got these modern AIs that can write a beautiful poem, they can write working code, but then you ask them to solve a tricky logic puzzle like a Sudoku, and they just fall flat on their face. It's the strange disconnect in their abilities that's really the core problem we're going to unpack today.
So let's talk about AI's reasoning problem. Right now, the kings of the hill are large language models. You know them as LLMs, and they're unbelievably powerful, for sure. But as the research behind this explainer points out, they've got this kind of hidden fundamental weakness when it comes to actual deep multi-step reasoning.
To get around this weakness, researchers came up with this really clever technique called chain of thought. The best way to think about it is like when you had to show your work in a math class. The AI literally thinks out loud by writing down its reasoning step by step. It turns one big, complex problem into a bunch of smaller, simpler text predictions that it can handle. And right now, that's pretty much the dominant way we get AIs to reason.
But here's the catch with chain of thought. It's incredibly brittle. It's like a house of cards. Because the whole thought process is just a string of text. One tiny mistake, one little wobble early on, and the whole thing just collapses. The ideal, what we're all really aiming for, is something called latent reasoning. That's where all the thinking happens internally, inside the model's hidden mind, much more like how we do it.
And hey, don't just take my word for it. The very researchers who built this new model, they put it really bluntly in their paper. They said that chain of thought is, quote, a crutch. They see it as a band-aid, a temporary fix, not the real long-term answer to cracking AI reasoning.
So this gets to the heart of the matter. Even though these AI models are gigantic, they are, in a way, paradoxically shallow. Think of it like this. They're a mile wide, but an inch deep. Their core architecture just has a fixed depth. That means they're fundamentally not built to do the kind of really deep step after step after step thinking you need for complex planning or tough logic puzzles.
Okay, so if the current architecture is the problem, where on earth do you look for a better one? Well, maybe the answer isn't in a bigger computer chip, but in the most powerful and efficient reasoning machine we know of, the human brain.
So the researchers went to neuroscience, and they pulled out 3 key principles. First, this idea of hierarchical processing. You know, how our brain has high-level parts for the big picture and low-level parts for the nitty-gritty details. Second, temporal separation. The fact that these different parts run at different speeds. The planning is slow, but the execution is fast. And third, recurrent connectivity. Those feedback loops that let us think and rethink and refine our ideas.
So they took these ingredients from the brain, and they built something totally new. And this is where we meet the hero of our story, the Hierarchical Reasoning Model, or just HRM.
Now, HRM is a completely different kind of beast. It's not just another LLM with a new name. It's a recurrent architecture, which means it has these internal loops that let it basically chew on a problem over time. It's built from the ground up for that deep internal reasoning we were talking about, so it can solve problems in one single pass without needing that fragile chain of thought crutch.
Okay, so we've got a new contender in the ring. It sounds good on paper, but how does this little brain-inspired model actually do when you put it up against the Goliaths of the AI world, the massive models we all use every day? Well, let's look at the tail of the tape.
First off, let's just talk about size. This HRM model, it has just 27 million parameters. Now, to put that in perspective, a big model like GPT-4 can have over 1 trillion. So this isn't David versus Goliath. This is like David versus an entire army of Goliaths.
So, round 1. They gave them extremely difficult Sudoku puzzles. The result for the biggest, best LLMs using chain of thought? A big, fat 0. Nada. A complete failure. And our tiny HRM? It solved 55% of them. And get this, after being trained on only 1,000 examples.
Okay, maybe that was a fluke, right? So next up, they tried finding the single best path through a really complex maze. Once again, the giant model scored a 0. They just couldn't do it. But the HRM, It found that perfect path almost 75% of the time. I mean, this isn't a small improvement. This is the difference between impossible and possible.
And this isn't just about fun and games. They tested it on the ARC-AGI challenge, which is a really key benchmark for more general, flexible intelligence. And again, the tiny HRM comes out on top. With no pre-training and just a handful of examples, it beats out even massive models like Claude 3.
So the results are, well, they're pretty shocking. The little guy won, and won decisively. Which brings us to the really big question: how? What's the secret sauce here? What is going on under the hood that makes HRM so good? The answer comes right back to that brain-inspired design. HRM is basically made of two parts that work together. You've got a high-level module, let's call it the planner. It works slowly, deliberately, thinking about the big-picture strategy. And then you have a low-level module, the worker, that moves at lightning speed, just crunching the numbers and handling all the details. It's like a really thoughtful CEO leading a super fast and efficient team.
And the way they work together is this really elegant dance. The planner sets a small goal. The worker then just computes like crazy to solve that one little piece of the puzzle. The worker reports back, done, here's the answer. The planner takes that information, updates its master plan, and then gives the worker its next task. And this loop, this cycle, just repeats, allowing the model to think incredibly deeply without ever getting lost or becoming unstable.
But hang on, because this is the part that is just, it's incredible. This isn't just about clever engineering. See, the researchers didn't program the model to organize itself like a brain. They just trained it to solve puzzles. And in the process, the model spontaneously taught itself to organize its internal structure in a way that mirrors a real biological brain.
So just look at this. There's this concept called dimensionality, which is basically a fancy way of measuring how much thinking space a system uses. In a real mouse's brain, the high-level planning areas have high dimensionality. They're complex and abstract. The low-level parts that handle details have low dimensionality. They're more focused. And what's amazing is that after training, the HRM did the exact same thing on its own. The planner part developed high dimensionality, and the worker part developed low dimensionality. This wasn't designed, it emerged. It's like they stumbled on a fundamental principle of how intelligence organizes itself.
So let's zoom out here. This isn't just another incremental improvement in AI. The success of this HRM model could have massive implications for the entire field. It might just be pointing us toward a whole new future for how we build thinking machines.
So what's the big takeaway? Well, for one, this shows us there's a path forward for AI that isn't just about make it bigger. We can build smarter, not just larger. It also points to a future where we have much more efficient models that can learn incredibly complex things from a tiny amount of data. And it throws down a real challenge to that chain of thought approach that's been dominant for so long. It gets us a step closer to what computer scientists call Turing-complete systems. AIs that are so flexible they could, in theory, compute anything a computer can.
And that really brings us to the final thought I want to leave you with. The HRM didn't just copy the brain's blueprint, it independently learned a fundamental principle of how a brain organizes itself to think. So the question this whole thing leaves us with is a really big one. If AI can learn to reason like a brain, what else is it on the verge of learning to do?